In my lecture 7 of this chapter, I have given one problem to solve to the viewers. Now in lecture 8 of this chapter, KTGS or kinetic theory of gaseous state, I like to solve this problem so that these two viewers can compare with my result with their own calculated value. And the problem, you can remember this calculate percent of oxygen molecule at 300 Kelvin that have speed 500 meter per second to 510 meter per second. And this problem has to be solved on the basis of Maxwell's distribution, Maxwell's speed distribution formula, and this speed distribution formula is that dnc by n equal to 4 pi and m by 2 pi kt, or we can write this capital M divided by twice pi RT and 3 by 2 e to the power minus mc square by twice RT. M the molar mass of this gas, R the molar gas constant, is the temperature, and here it is C square addition. We have the data, this M equal to 32 into 10 to the power minus 3 kg mole inverse in SI unit. T is equal to 300 Kelvin and C is here 500 meter second inverse, and DC equal to 10 meter second inverse. So if we put all these values, then, and this one is the fraction of molecules that have speed c within range addition. You see, this also I can say the probability of a molecule to have the speed C to C plus dc at a temperature T, and the gas is having the molar mass M. Now we insert all these values. So dnc, so this one equal to 4 into 3.14 into 32 kg mole inverse divided by 2 into 3.14 into R in joule, 8.31 joule mole inverse Kelvin inverse to the power 3 by 2 and e to the power minus 32 into 10 to the power minus 3 kg mole inverse into C means 500 meter second inverse square and divided by 2 into 8.31 joule mole inverse Kelvin inverse into 300 Kelvin into 500 C square 500 meter second inverse square into DC 10 meter second inverse. So we can write here this dNc by n equal to 4 into 3.14 into, we can replace this joule. Joule is equal to kg meter square second inverse 2. So if we replace the joule here and this case by this kg meter square second inverse 2, then it will give you 32 into 10 32 into 10 to the power minus 3. 2 into 32 into 10 minus 3 kg mole inverse divided by 2 into 3.14 into 8.31, and instead of joule we can write here kg meter square second inverse 2, and again it is the mole inverse Kelvin inverse, and here 300 Kelvin to the power 3 by 2. Then it is 32 10 to the power minus 3 kg mole inverse. Here 2 into 3.14 into 8 into 8 into 3.14, and this one joule here, and mole inverse Kelvin inverse, and T is 300 Kelvin. And in this case, and the exponential term e to the power minus 32 into 10 to the power minus 3 kg mole inverse into 500 meter second inverse square, and divided by 2 into 8.31, and instead of joule we can write this kg meter square second inverse 2, and then again mole inverse Kelvin inverse, and instead of T we can write 300 Kelvin, and here again 500 meter second inverse to the power square into 10 meter second inverse. So all the data I think have been inserted here. 32, this one. If we calculate this numerical value, then this one will give you this 4 into 3.34 into 3.14, and this will give you the value 2.922, and this numerical value gives you 2.922, and into 10 to the power minus 9, and if we cancel the like units, then mole inverse, Kelvin inverse, Kelvin, so it is 3 by 2. So we can write here this meter second inverse minus 3, and this exponential value is 0.201, and it is unitless, kg, meter square, and second inverse 2, mole inverse, Kelvin inverse, and multiplied by 225, and here 10 to the power 4, and here 10 into 10 to the power 5 meter second inverse and cube. So this value also cancel, these units are cancelled, and gives you the value 0.01844, or in percentage, whenever it is multiplied by 100, you can get this percent, and percent is 1.844%. It means that this is the answer. It means that out of 10,000, out of 10,000 oxygen molecules, only 1,844 molecules at 300 Kelvin had speeds 500 meter second inverse to 510 meter second inverse. So this is the problem 2.922 into 10 to the minus 9. Here it is 0.20 as this value. So this calculation, viewers are requested to compare these calculations with their variance. Now we are coming to explain the salient features of this Maxwell's speed distributions law. And Maxwell's formula for the speed distribution is dnc by n equal to 4 pi, and we can also write in terms of molecular mass m, and here 2 phi and kT to the power 3 by 2 into e to the power minus mc square by twice kT and c square kTc. Again, I can mention that this is the fraction of the molecules or probability of a molecule to have the speed C to C plus dc at a temperature T, and the gas is having the molecular mass M. So this you can write also this Fc into dc, where Fc is called the speed distribution function. Speed distribution function, and that means it is actually 1 by n dnc by dc. It is the fraction of the molecules having the speed c within range 1, within the range divided by dc. And it is the expression of Fc is 4 pi m by twice pi kt to the power 3 by 2 e to the power minus mc square by twice kt and c square. Since c is much greater than 1, range is very small, range is unit range, so we can Fc we can define the fraction of the molecules having the speed c at a temperature T, and the M is the molecular mass of this gas. Now you can see the for a given gas M is fixed. At a given temperature, T is also fixed. Then actually Fc is a function of C only for a given gas at a given temperature. Say we can make a table for a particular gas at a given temperature. We can put the various values of C ranging from this very small to very high. We can calculate this Fc distribution function. So we can make a table. We can also make a table. Say for oxygen gas at 300 Kelvin, and here C and here Fc. We can put the different values of C here, and here. We can get the magnitude of Fc. Now, whenever C equal to 0, Fc equal to 0. And when C equal to C1, it is the Fc1. C equal to C2, it is Fc2. And C equal to C3 and F equal to Fc3, and dot. When C tends to infinity, very high value, Fc tends to 0. So this is the table. And this formula actually contains will give you the various informations regarding the speed distribution of the molecules of a gas at a particular temperature. So if this table is projected in a diagram, Fc versus C, then all the informations will reveal before you, and all the information you can get it from this diagram. And if we draw here in the x-axis the speed, and here it is FC, and it is origin. And it is origin. So we are drawing this FC versus C. C is independent variable, and so it is plotted along this x-axis, and here FC is dependent on C, so FC is plotted along this y-axis. So if we plot how the plot looks like, this curve will start from origin. Curve will, when C equal to 0, FC equal to 0. And then again, whenever the C is increased along this x-axis, then these two terms, this is the one term, and this is C square, this another term. And this one is non-exponential term, and this one is exponential term. C is present in these two terms. With increase of C, this term will increase the value of FC. But with the increase of C, this term decreases, so this term will decrease this value of this FC with the rise of C. So this actual or the value of FC depends on relative magnitude of these two terms, and this sort of expressions is very popular and called the Gaussian. This called the Gaussian distribution. In the expression of FC, there are two terms. One term is increasing, other term is decreasing with the increase of C. So naturally, in this case, whenever the value of C is low, then the non-exponential term will dominate over the exponential term, and with the increase of C, for the low value of C, FC will begin to increase. So this term will begin to increase, FC begins to increase. When the C is getting higher and higher values, the exponential term again begins to dominate, and this term with the increase of C, this term will decrease, and so FC also decreases. So this curve will be like that, increasing and then attains maximum and then decreasing to the asymptotic value. Asymptotic value means with the increase of C, high value of C, FC also, this curve runs parallel with this C axis, and they will meet only at infinite value of C. Means at finite value of C, this curve will not meet this C axis. So you see, whenever the C is very large, then FC also, C is very large, trying to infinity, then FC is also very small. Another thing I can say, at a given speed, FC attains the maximum value. Say this is the C dash. This is the speed at which this FC attains maximum. and this C we can call most probable speed at which the FC value maximum. It means that the maximum or the maximum fraction of the molecules will have this speed at at a particular temperature and for a particular gas, and this speed we call most probable speed. So the features comes up when C is equal to 0, Fc equal to 0, and the 2 when C tends to infinity, Fc tends to 0, and third one when C equal to Cmp, most probable speed, then Fc is maximum. These are the three informations we can get from this value. So it means that if we illustrate these three informations, then you can find there is no molecule at a given temperature for a gas have a zero speed. Means no molecule is at rest. All the molecules are moving with variety of speeds in all directions with equal probability, and no molecule will be rest at any particular temperature. So this one information, and second information is that the molecules are having very, very high speed, or the fraction of the molecules having very, very high speed is also very few. Only a small fraction of the molecules will have the speed having very large values. And the third one, whenever at a particular speed, which we call the most probable speed, at which the maximum fraction will have that speed. So you can see this type of informations also very popular in a financial or economic scenario of a country. In a country, you could not find a person who is penniless. No, you could not find a person who is penniless, and also you could find only a few people or few persons who have billions of money in their possession. Most of the persons in a country will have one common income, and this common income, that those people which have a common income, maximum fraction of the people will have the common income, and these people are called the middle class. In any country, you can see the number of persons in middle class will be very large, and no person you can find which are penniless, or very few persons will have millions of money. So this scenario is also equally applicable in a financial position of the people in a country. Or another example I can give you. Say, another example. Suppose in a class, the students are appearing in examination, full marks 100, and after getting this result, you can see no student will get this 0 mark, and very few students will get this mark near to 100. Most of the students will get a common mark, and which are ranging depending on temperature and the gas. And you can also, if you like so, you can also draw the distribution curve. You first make a table and then do a distribution curve, and distribution curve will be like that. Distribution curve, you can see, say, here the fraction. Here the fraction of students appearing in examinations. Here the mark. Then the fraction of the students are having, suppose the 100 marks we can get it in 10 slabs, 0 to 10, 10 to 20, 20 to 30, and the persons and the fraction of the students are having the 0 to, this is 0 to 10, and fraction of the students 10 to 20, and the fraction of the students 20 to 30, and fraction of the students 30 to 40, and the fraction of the students 40 to 50, and fraction of the students 50 to 60, and fraction of the students 60 to 70, and this is 70 to 80, 80 to 90, and 90 to 100. You can get this slab. 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70, 70 to 80, 80 to 90, and 100. And if you draw this and if you take this average curve, then you will have this similar type of distributions. You can do it by yourself, taking the marks of a large number of students appearing in examinations of full marks 10, and making this slab of a 10 marks interval. Again, another thing, suppose here it is the fraction of the molecules having this speed C dash. Fraction of the molecules having this speed C dash. And if we make a small range, suppose this one is C dash plus C dash plus DC. DC the range. DC the range. The fraction of the molecules having the speed C dash is this one, and this is the range. So this one, this ordinate is the FC dash. And if you multiply by this range DC, then it is one arm, and this is another arm. So product of this two will give you this area. This will give you the area. What this area represents. The area represents FCDC. The area represents the fraction of the molecules having the speed C dash within the range DC. So if you vary the c dash from 0 to infinity, then it will give you the full area, and full area under this curve will give you the full fraction of the molecules, means 1. Full fraction of the molecules is equal to 1, means the area will be equal to 1. Then again we can draw another sort of curve. This sort of curve. Suppose here it is C, and here it is FC, and here this curve starts from origin and increases and then becomes asymptotic with this C axis. This is origin. Suppose here the fraction of the molecules, this ordinate will represent the fraction of molecules having this speed C dash. So it is the C dash. If we like to calculate the fraction of the molecules having the speed greater than or equal to C dash, if you like to determine the fraction of the molecules having the speed C dash to infinity equal to C dash or greater than C dash, means C dash to infinity, then it will give you this curve, this area. This will give you the area of the right hand side of the ordinate. Right hand side of this ordinate, and ordinate is drawn at this C dash. And similarly, if we like to calculate the fraction of the molecules having the speed less than or equal to C dash, speed less than or equal to C dash means 0 to C dash, the fraction of the molecules having the speed 0 to C dash, then it will give you, it will be the area. It will be the area of this curve. It will give you the area of this curve. And since total area is equal to 1, this fraction and this fraction, sum of these two fractions becomes equal to 1, and full fraction, all the molecules are coming up from this of the speed C0 to infinity. So in this way we can show the various salient features of this distribution curve. Now I am coming to now the effect of T, and M is fixed. For a particular gas, we like to see what is the effect of temperature on this distribution of speeds among the molecules. So in this case, say we draw the curve, here C, the speed, here origin, and here it is FC. So this curve would, suppose we have considered only the two temperatures, one is lower temperature and other is high temperature. So at lower temperature T1, this curve becomes like this one and attains the maximum, and then it is decreasing to an asymptotic value. This is at this T at the temperature T1, and this one is CMP at this temperature T1, at this temperature T1. In this case also you can see these are the two factors, two terms. Here also you can consider the two terms which contain this temperature. Mass is fixed. So this is one term and this is another term. At low T, actually at low T, this term low T, this term is high and this term is low. So whenever the temperature at lower temperature T1, this curve will dominate, and this curve will be increasing very rapidly, and then due to the presence of C square, again this term is coming down, falls from this maximum value to an asymptotic one. If you at high T, if the temperature is, suppose this is T1, this is T2, at high temperature, this curve, high temperature, this curve is low, and this curve is high. So this curve is low, non-exponential term, and this is exponential term. Non-exponential term is decreasing with this increase of temperature. So at this T2 temperature, which is hot temperature, this curve will come below this lower temperature curve. And you can see another thing here. In a single term, you are having these two factors. One is T and other is C square. T is increasing. This term will increase this value, this one, and so this value is increased. Again, C square, whenever the C is increasing, this term will dominate, C square term will dominate, and this value, C square, will try to decrease this value of the exponential term, and so Fc increases. So one term is increasing, other term is decreasing in a single term. So the net effect is that the curve will be this curve will be broadened. This curve will be broadened and not falling very rapidly with this at this high temperature. So this is at the temperature T2. This is at the temperature T2, and T1 is less than T2. And with the increase of temperature, this curve becomes more flat, more shallow, and more uniform. At the lower temperature, this curve is narrow. So this one you can say this one is the CMP at this temperature T. So you can see another information, effect of temperature when T is less than T2, FCMP CMP at a temperature T1 is less than CMP at this temperature T2. It is quite obvious as the temperature is increased, the financial conditions, the thermal energy of these gases will be increased, so more molecules will try to achieve this higher speed, and so most probable speed is also higher. In case of economic scenario, the middle class people in America is much higher. Income of this middle class people in America is much higher than the income of this middle class people in India, as America is having the much more economic resource. Another thing you may notice here, the fraction of the molecules have this speed CMP at this temperature T1 is high. So it is FCMP at this temperature T1, and but here at this high temperature, this is CMP at this temperature T2 is lower. So fifth condition, you can write this CMP T1 is less than T2, and also FCMP at this temperature T1 is greater than FCMP at this temperature T2. So at lower temperature it is a highly narrow curve, so maximum more fraction of the molecules having this most CMP. As the temperature is increased, though the most probable speed is increased, but the fraction of the molecules having the most probable speed at high temperature is low. But one thing you can see from this graph, the fraction of the molecules having this speed near to most probable speed are also high. The fraction of the molecules having this speed near to most probable speed also very high. And another thing I can also show you, suppose this is the speed C dash. So if you like to find the fraction of the molecules having the speed greater than or equal to C dash, at lower temperature it is this area. This area will give you the fraction of the molecules at T1 temperature having the speed C dash to infinity. But with the increase of temperature, this area will be greater. Means a fraction of the molecules having the high temperature T2 at the high temperature T2 having the speed C dash to infinity is getting much more. Actually, more molecules will get the speed higher than C dash. And similarly, you can say that the fraction of the molecules having the speed 0 to C dash is greater at T1 and less in T2 temperatures. And another two factors I like to mention here. Say, if you increase this temperature more and more, and more, then this curve becomes more shallow and shallow, becomes more flat, and the speed becomes more and more uniform. At the very, very high temperature, this curve will lie along this C-axis, and so it means that all the molecules will have the same speed at very, very high temperature. And again, if the temperature is very, very low, as the temperature is decreasing, this curve is coming towards this left hand side, and when temperature is 0 Kelvin, whenever the temperature is 0 Kelvin, you can see the curve lies along this y-axis, means x-axis. It means that all the molecules have this speed 0. So it is a prediction of the kinetic theory of the gas, that at 0 Kelvin temperature, all the molecules at 0 Kelvin temperature, all the molecules are at rest. There will be no movement. This is also one of the prediction of the kinetic theory of gas, and it is also shown here from this graph. And last one, I like to mention the effect of temperature, effect of molecular mass when temperature is fixed. When temperature is fixed, you can see from this expression, temperature and molecular mass, they are present in reciprocal fashion. So the effect of molecular mass will be opposite to that of this temperature. When this temperature, so this is, if you consider this is M1 and this is for this M2, then M1 is greater than M2. Means lighter gas, in case of lighter gas, there will be uniform speed distribution than it is heavier gas. So it is for suppose helium, and it is for suppose argon. More and more the molecular mass of this gas is high, it becomes more, the curve will be more narrow, and lighter gas will have the broader curve, uniform distribution, more and more uniform distribution of speed. So I have explained all this, I have tried to explain all the salient informations which are mysteriously hidden within this formula. If we draw this diagram, then all these mysteriously hidden informations are coming out, becomes very clear to us. So this is all about my today's lecture, and in my next class I shall try to explain the different speeds of the gas molecules and their relative magnitude, and like to show all these speeds, say most probable speed, average speed, root mean square speed in a Maxwell's diagram like this one. So thank you all for watching this video.